This single unbroken curve touches every point in the square. Every point. Pick one with a pen, zoom in as far as you like, and the curve goes through it. There are no gaps hiding between neighboring strands. Somehow, a one-dimensional line fills a two-dimensional region, and the reason it can do that is being withheld for just a minute. Here's the finished object beside an ordinary curve. The ordinary one can twist, loop, and scribble furiously, yet you can still point to open patches it missed. The other curve leaves no such patch. Its image is the whole square. That sounds like a contradiction. A curve has length, and a square has area. A curve should be too skinny, and if we try to draw this with a pen, we would fail immediately because the ink has thickness, so strip the ink away. Mathematically, a curve means a continuous function whose input is one number, running from 0 to 1. The output is a point in the square. As that input slides forward, the point moves continuously, no teleporting. The astonishing claim is that every location in the square appears somewhere along that trip. This is a Hilbert curve, or more precisely, the limiting Hilbert curve. What you see first is an approximation because a completed curve contains infinitely much detail. Keep zooming and the same folded structure keeps returning. And here's the part I want to get hold of. Infinity alone doesn't explain anything. Plenty of infinitely complicated curves still miss almost everything. So what tiny repeatable instruction forces this particular path to cover every last point? The whole construction begins with 4 rooms and one rule about doorways. Divide the square into 4 equal smaller squares. We want one continuous path that enters each room exactly once at this level, so connect their centers in a U shape, lower left, upper right, lower right. That little U is nowhere close to filling the square. Good. Its job is to tell us the visiting order. Now divide every room into 4 rooms of its own. Put a smaller U inside each large room, then connect the 4 copies into one path. 2 copies have to rotate so their endpoints meet their neighbors. That rotation is the small hinge holding the entire construction together. Ignore it and the path breaks into pieces. Repeat. Each room receives 4 smaller rooms. Each small room receives its own correctly oriented copy of the path. After 1 round, the curve visits 4 cells. After 2, 16, then 64. After round n, it visits 4 to the end cells, threading their centers in one uninterrupted order. Watch the 4th round run for a moment. The path enters a cell, folds through its 4 children, exits through the required side, and performs the same maneuver again next door. I love how little the rule knows. It has no global map of the finished monster. Each copy only knows where to enter, where to leave, and how to visit its 4 children, but cell centers are still only finitely many points. Even after a million rounds, there are gaps, absurdly tiny gaps, but gaps all the same. The claim was, every point, with no exceptions, so the finite drawings cannot be the answer. What exactly survives when the number of rounds stops being finite? What survives is a sequence of motions that settles down everywhere at once. Imagine a dot traveling from time 0 to time 1 along the first U. At the next stage, we replace that trip with the 16-cell trip, keeping the same start and finish. Then we replace it again. The path changes, but the correction gets smaller. At stage n, every altered piece is trapped inside a cell whose width is 1/2 to the n. The new position can differ from the old one only by the diagonal of that tiny cell. Those diagonals shrink to 0. This gives us a limiting position for every time t. Call it h of t. The shrinking bound works across the whole journey, so the approximations converge uniformly. That word earns its keep. It says one sufficiently late stage approximates the completed curve well at every time, rather than going feral somewhere hidden. Each finite path is continuous. A uniform limit of continuous functions is continuous. Therefore h is continuous. Slide the time by a tiny amount and the point in the square moves by a tiny amount. No jumps appear during the infinite process. That closes one loophole. We genuinely have a curve, not a teleportation schedule disguised as one. Yet continuity still doesn't give us the square. A circle is continuous and misses nearly everything inside it. A spiral can win forever and still leave points untouched. We need a stronger fact tied to those nested rooms. Take any target point in the square. The construction gives us a room containing it, then a smaller room inside that one, then another. Can we use that descending address to force one moment of the journey onto the target exactly? Yes. The target's nested rooms also trap a nested sequence of times. At the first stage, 1/4 of the journey is assigned to each of the 4 large cells. Choose a cell containing our target point. If the point lies on a boundary, there may be 2 choices. Pick either one and keep going. Inside that chosen cell, 1/4 of its time interval belongs to each child. Choose a child containing the target. Repeat forever. The spatial cells shrink around the point and the matching time intervals nest inside one another. Their lengths are 1/4, 1/16, 1/64, continuing down to 0. Nested closed intervals with lengths shrinking to 0 share exactly one time. Call it T star. Now look at h of T star. At every resolution, T star belongs to the interval assigned to the selected cell, so h of T star must lie in that cell. The cells themselves collapse onto our target point. There is nowhere else for the curve to land. H of T star equals the target. There it is. That's the piece that gets me. We never hunt through an impossibly tangled finished curve. We take the point's address, digit by digit, and the construction manufactures a time that reaches it. Because the target was arbitrary, h reaches every point in the square. The mathematical word is surjective. H maps the entire interval onto the entire square. Now the original claim is proved, and it immediately creates a new headache. If every point gets a time, have we somehow paired the line and square perfectly? Could we reverse the map and recover one unique time from each point? The boundaries are already hinting that something messy happens there. The reverse map fails because some points are visited more than once. Those cell boundary choices can produce different infinite addresses, and different times may collapse onto the same location. So this curve is a continuous surjection, not a perfect continuous pairing. That distinction resolves a lot of the apparent paradox. If we demanded a continuous one-to-one correspondence with a continuous inverse, the interval and square could not have one. Their topological dimensions really are different. Remove one interior point from an interval and it splits into two pieces. Remove one point from a square and you can usually walk around the whole. Their basic connectivity behaves differently. The Hilbert map escapes by folding the interval onto itself in the image, over and over at every scale. Information gets merged. You can go from a time to a point continuously, while a point does not always tell you which time produced it. And the length? The finite approximations grow longer without bound. At order n, the path makes roughly 4 to the n steps, each with length on the scale of 1 over 2 to the n. Multiply those and the total grows on the scale of 2 to the n. The limiting curve has infinite length. It pays for area with endless folding. Careful though, infinite length by itself still doesn't guarantee positive area. Plenty of wild curves have infinite length and cover no region. The nested cell assignment is doing the real work. There is one more apparent offense. A continuous curve from an interval usually feels like a one-dimensional object, yet this image has area 1. So which dimension does the Hilbert curve actually have? The answer depends on whether we mean the parameter space, the image, or the local scaling law, and that local law leaves a very clear fingerprint. The fingerprint is this: shrink the time interval by a factor of 4, and the corresponding piece of the square shrinks in width by only a factor of 2. Time and distance scale at different rates. After n rounds, a time interval of length 4 to the minus n controls a cell with width 2 to the minus n to square root of the interval's length. So spatial distance behaves roughly like the square root of the time difference. Close times have close images, but on a square root scale, not the usual straight line rule where halving time halves distance. The curve can move aggressively at tiny scales. That roughness lets it spread through area. In the language of Holder continuity, the exponent is 1/2. That matches the jump from one parameter dimension to a two-dimensional image. 1 divided by 1/2 equals 2. Almost suspiciously tidy. Box counting gives the same result. At scale 1/2, the curve occupies 4 boxes. At 1/4, 16. At 1/8, 64. When box width is epsilon, the number needed grows like 1 over epsilon squared, the scaling of a two-dimensional set. The completed Hilbert curve fills the square, so its Hausdorff dimension is 2, and its area is positive, while its input interval remains one-dimensional. A continuous map can increase dimension when it is sufficiently non-injective and rough. Now this stops looking like a drawing trick and starts looking useful. We have a rule that turns one number into a location in 2 dimensions while keeping nearby times reasonably nearby in space. That strange compromise, especially the word reasonably, is why versions of this curve appear far outside pure geometry. That compromise gives the curve a practical job. It can turn a two-dimensional neighborhood problem into something close to a one-dimensional ordering problem. Suppose a database stores millions of locations. Sorting by X tears apart points just across a vertical boundary. Sorting by Y does the same horizontally. A Hilbert index assigns each grid cell a position along the curve. Sort by that index, and points near each other on the list tend to be near each other in the plane. The guarantee runs one way: nearby times map to nearby places. Nearby places may sit far apart in the ordering, especially across cell boundaries. Still, that locality helps spatial databases, image processing, memory layouts, and workloads distributed across machines. Here's a concrete way to understand the parameter. Write time in base 4. Each digit chooses one of 4 child cells. The next chooses a grandchild, with orientation adjusted by the recursive rule. An infinite digit string becomes an infinitely precise address in the square. Run the digits forward and one number becomes a point. Read the nested cells geometrically and a point yields at least one compatible time. The proof is hiding in that address system. So return to our opening curve. It looked like a line swelling into a surface. What happened is more exact and prettier. Every fragment of time was repeatedly assigned to a smaller room. Continuity came from the rooms shrinking uniformly. Complete coverage came from every point owning a nested chain of rooms. A line cannot become a square through smooth, reversible stretching. This construction folds, revisits, and loses information at infinitely many scales. Because those folds are organized with absurd care, nowhere in the square remains for a point to hide.